Here we're going to start out with section 8.2, and we'll also fit in 8.3 into this. So, to make detailed measurements or to conduct experiments that can't be performed on a patient, what we want to do is we've still got to make the measurement, but we obviously don't want to do it on a live or, for that matter, a dead body. So, what do we do in order to be able to try to get an idea as to what these measurements are actually going to be? And what we do is we find something that'll substitute for a patient, and that's referred to as a phantom. The chief characteristic is going to be their shape and composition. The phantom material is designed to mimic the patient with respect to radiation scattering and absorption. And so that obviously is going to depend on the type of radiation to be used. So this gives us an idea as to what sort of dose we're going to end up with. So we got two types. We've got geometrical and we've got anthropomorphic. A geometric phantom is going to be in the form of some simple geometrical shape and makes little attempt to imitate the shape of the patient. You could have cubes, rectangular slabs, cylinders, whatnot. An anthropomorphic phantom is designed to duplicate the shape of the average patient and perhaps even the distribution of materials within the patient. So the term tissue equivalent is defined as meaning that the material has the same or very similar radiation properties as tissue with respect to a specific type of radiation. Water is considered to be the best substitute for soft tissue for most types of radiation. Important properties of the phantom material include the elemental composition, the electron density. Compounds or mixtures are often described in terms of the effective atomic number. This is a single value of the atomic number that will correctly describe the absorption and scattering properties of X-rays over a reasonably wide range in energy. When the Compton effect dominates, the mass attenuation coefficient depends only on the electron density, which is almost independent of Z for materials with little or no hydrogen content. When the photoelectric effect dominates, the attenuation coefficient is highly sensitive to the value of Z. Effective value of Z is 7.8 for air and 7.5 for water. The value of tau divided by rho, or the photoelectric mass attenuation coefficient, at 20 keV is 0.544 cm squared per gram for water and 0.536 cm per gram for air. So you would expect the value of tau over rho to be slightly higher in air based on the effective values of Z cited above. And the fact is, it is not just shows the approximate nature of the effective Z value. Wait, I think I said that wrong. The fact is that it is not just shows the approximate nature of the effective Z value. Sorry about that. The compound lithium fluoride is widely used in TLDs. The effective Z for lithium fluoride is 8.3, and its electron density is 0.833 times that of water. At an energy of 1 MeV, the Compton mass attenuation coefficient is this value for lithium fluoride and this value for water. So you can see here that it's a little bit lower for lithium fluoride than that of water. The ratio of these two mass attenuation coefficients is just above the value expected based on the ratio of electron density of lithium fluoride to that of water. Geometrical phantoms are usually homogeneous. They often are made of solid materials like polystyrene, acrylic, lucite plexiglass, polymethyl methacrylate, or perspex, which I've never heard of relative electron density of 0.972. Solids are convenient. They can be set up quickly, do not require that the detector be waterproof. An epoxy resin, phantom materials are sometimes referred to as solid water, which for most people will say, what are you talking about, ice or virtual water? Slabs of this material are 30 by 30. My guess is you've probably seen this as the physicists have dragged this out to do a QA, perhaps muttering under their breath while they're doing it. And they come in varying thicknesses. Slabs are available, which are machined to accept various types of ion chambers. By using different combinations of plates, various ion chamber depths are possible. Water phantoms are commonly used for radiation therapy dosimetry purposes, especially for radiation calibration and beam measurements. Water is considered the best substitute for tissue in megavoltage beams. A water phantom is essentially a large fish tank that can be filled with water. And computerized scanning water phantoms will be discussed in Chapter 9. Anthropomorphic. Okay, let's try this again. Anthropomorphic. There we go. Phantoms are designed to imitate the shape of the patient. An example is the rando phantom, which is constructed to form a tissue equivalent resin modeled around a natural skeleton. This phantom has natural air spaces, which are taken from impressions of a cadaver. Rando has realistic lungs, and he can be purchased sectioned into 2.5 cm axial slices. Within each slice, there are plugs arranged in a 3x3 square centimeter grid, which may be removed and placed by TLDs. Let's see if we can find a picture of old Rando here. They said 8.2. There we go. And it's sectioned into slices 2.5 cm thick. And you can put in TLDs in certain spots there, which is kind of cool. Okay, now you'll notice here 8.3 covers gas, 8.4 colors solid, and 8.5 colors liquid. And then 8.6 finishes up with the neutron survey meter. So now we're going to go into the gas detectors. So all gas ionization chambers rely on the ability of radiation to ionize a gas, producing pairs of ions. In the absence of radiation, no current will flow in the circuit, shown in figure 8.3. So when radiation passes through the gas between the charged electrodes, it produces ion pairs, which are attracted to the plates having charges of opposite signs. As that charge is collected, it will register as a current on the ammeter. So in the absence of radiation, no current will flow because charge is unable to flow across the gap between the electrodes. When charged particles pass through the detector, they produce ion tracks consisting of pairs of oppositely charged ions. The ions will be attracted towards the electrode that has the opposite charge. Small electric current is produced from the collection of these ion pairs, and gas ionization detectors have low efficiency compared to solid state detectors. That means the amount of current or total charge registered by the ammeter is relatively small in comparison to that measured from solid state detectors for a fixed amount of radiation. The density of the ion tracks is much lower in a gas because of its low mass density and low Z value. So, in an ionization chamber, the charge is collected by the electrodes. If the chamber is irradiated with photons, and if the collecting volume is in charge particle equilibrium, and if the mass of the gas irradiated can be accurately determined, then the exposure can be determined directly. Ionization chambers have a flat energy response for photons above 100 keV. That means that the charge collected depends only on the exposure and not on the energy of the photons. If the charge produced by the ionizing radiation is Q, then Q divided by X is independent of the energy above 100 keV. An ionization chamber can be used to detect the ionization produced by the passage of charged particles as well as photons. In fact, an ionization chamber cannot distinguish between them. So, free air ionization chambers are used for exposure measurement in national standards laboratories such as the NIST, National Institute of Standards and Technology. These instruments are impractical for field use, so the NIST sets U.S. national standards for radiation quantities and measurements and can be described as a primary standards laboratory. So we've got a diagram down here of a free air ionization chamber. The X-rays enter the chamber from the left. Ions are produced all along the volume. So you got the X-rays coming in here, and then you've got electrons being produced. They're coming in and they're also exiting. So the charge is collected from the volume labeled collecting volume, this volume right in here. The exposure is to be measured for the volume labeled sample volume. Some of the charge produced in the sample volume may leave it, provided every charge that leaves the collecting volume is replaced by one entering, so that gives you CPE. Then the charge produced in the sample volume will be the same as that collected from the collecting volume. In this way, all the charge collected may be assumed to have originated by photon interactions in the sample volume. The wires and the guard plates are used to make the electric field very uniform, so the charge will only be collected from a well-defined region labeled collecting volume. See the wires over here, you can see the guard plates here, you can see the electrometer here, and you've got a voltage being applied here. So each photon produces one, or at most a few ionizations, but an electron set in motion by a photon may produce tens of thousands of ionizations when the timer comes to rest. The electrons produced by the photons move through the air, creating tracks of ionization. The point in the middle of the volume, labeled sample volume, is the place at which we wish to measure the exposure. We shall assume that the photon beam is not significantly attenuated along the length of the beam within the sample volume. So it'll be uniform throughout the sample volume. So to measure the exposure, we must collect and measure all of the charge produced as a result of photon interactions in the same volume. The gray volume that you saw before is called the collecting volume. The sample volume is the light blue region. Charge is collected from throughout the entire collecting volume by the electrode at the bottom. Some of the electrons produced in the sample volume by photon interaction escape from the collecting volume. The full ionization produced by the escaping electrons as they come to rest will not be collected. But for each one of these escaping electrons, it's replaced by another electron within the same energy, or with the same energy. Then there's going to be no net gain or loss. This is CPE. In this case, the charge collected will be equal to the charge produced by photon interactions in the sample volume. The distance from the sample volume to the boundary of the chamber must be greater than the maximum electron range in the air. If that's not the case, an electron could travel up and through the top plate and be lost to the collecting volume. The electron would not be replaced by an incoming electron, so you don't have CPE. So as long as the plates are far enough apart, all charge produced in the blue shape sample volume will be collected. The exposure can be calculated directly from this equation, where Q is the charge collected and M is the mass of the air. These are practical in the range of 10 to 300 keV. Above this photon energy, the range of maximum energy electrons becomes large, and the chamber must therefore be made quite big. So at above 3 MeV, the plate separation must be impractically large. The maximum range of electrons produced by 3 MeV is about 10 meters. That'd make a big chamber. So in radiation therapy, radiation beams often have energies higher than this, and therefore the quantity exposure is of limited usefulness. So a free air ionization chamber is an absolute dosimeter for exposure measurements. A free air ionization chamber measures exposure, but not dose, without comparison or calibration against other radiation measurement equipment. An absolute dosimeter is a radiation measurement instrument that does not need to be compared or calibrated against any other radiation measurement device. All right, cavity ionization chamber. So imagine an air cavity of mass M, something like that. It should be surrounded by a large air shell. The entire cavity plus shell is to be irradiated by photons. We want CPE, so the air shell must be thick enough so that the air cavity is not the buildup region of the air shell. If the air shell is too thin, then more electrons will leave the cavity than enter it. If the source of the photons were too close to the cavity, then there might not be CPE in the air cavity. So to achieve CPE, the thickness of the air shell must be larger than the maximum range of electrons set in motion by the photon beam. This is just like the free air ionization chamber. Then you can see here exposure is equal to Q divided by M. Same goal can be accomplished in a more practical way by replacing the air shell by a solid material that has an effective atomic number Z as close to as possible to air. Air has an effective Z value of about 7.8. The thickness of this solid wall must be large enough to provide CPE in the central air cavity, which is to say that the wall thickness must be greater than the maximum range of electrons set in motion in the wall by the incoming photons. We can think of this wall as solid air. As typical solids have a density of about 1,000 times the density of the air, it becomes practical to build such a device that can be used as a field measurement instrument. So the wall or shell needs to be only 1/1000th of the thickness of the air shell. And we would like the wall to be thick enough to provide CPE, but not so thick to significantly attenuate the incoming photon radiation. At low energy, a thin chamber wall is adequate to provide CPE and to minimize attenuation. At higher energies, a thicker wall may be necessary. Some ion chambers are provided with a buildup cap, which can be added for high energy radiation. Special buildup caps are available for cobalt-60 radiation. The thickness of the cap plus the thickness of the chamber wall is about 5 millimeters, which corresponds to the value of D max for cobalt-60 radiation. When the cap is added, the cap plus the wall will provide CPE. So you've got your air cavity, you've got the solid air shell around it. The solid shell is made from an air equivalent material that is thick enough to provide charge particle equilibrium inside the air cavity. They're generally calibrated against a standard such as a free air ionization chamber. They are compact, and it has the added advantage they can be used to measure other types of radiation such as electrons. For photon measurements in air, the ionization produced in the cavity originates from electrons that are produced in the buildup cap and the wall of the chamber by photons' interactions there. These secondary electrons travel the cavity, leaving a trail of ionization. If the ion chamber is instead placed in a medium other than air, such as a water phantom or a solid phantom, the buildup cap is removed and the secondary electrons are generated in the medium by photon interactions in the medium. So for primary electron beam measurements, a thin wall is desirable because of the irradiating particles themselves produce the ionization directly as they pass through the cavity. A thick wall would disturb the fluence of these particles. For electron beam measurements, the buildup cap should be removed from the chamber. Small cavity ion chambers can be used to make measurements in regions where the dose is changing rapidly with position. Such chambers have a high spatial resolution. Since the amount of gas inside such a chamber is small, it will suffer from low sensitivity. The amount of charge produced inside the cavity for a given amount of radiation will be small because the mass inside the mass of the gas inside the cavity is small. For large cavity ion chambers, spatial resolution is sacrificed in order to obtain high sensitivity. So you've got three major types of cavity ion chambers. You've got the thimble, flat cavity, and the well ionization chambers. And you can see these here. The thimble chambers, they are cylindrically shaped, somewhat loosely like a sewing thimble. Examples are farmer chambers, mini chambers, diagnostic energy chambers, survey meters. Flat cavity chambers are sometimes described as pancake pillbox or plain parallel chambers. They're shaped somewhat like a pillbox. Examples are the plain parallel chambers used in radiation therapy for electron beam measurements. The monitor chambers in the head of the linac, extrapolation chambers, so on and so forth. Well ionization chambers, they are used in nuclear medicine for radioactive source strength assay and in therapy for brachytherapy. Thimble chambers. Thimble ionization chamber represents a sewing thimble. And the chamber collecting volumes are pretty small, 0.1 to 1 cubic centimeter for therapy applications and up to 2,000 for survey meters. So you see a well ionization chamber here with an insert. Well chambers are used for brachytherapy isotope source calibration. A well chamber like this can be used to determine the activity of sources prior to implant in the patient to make sure you've got the right amount of activity that you need. The cable is attached to an electrometer. The sources are put into the insert, and the insert is lowered into the well. So you've got a thimble ionization chamber here where you've got the thimble wall, you've got a central electrode, you've got the stem, and then you've got insulators. So the inner thimble wall is coated with a conducting material, and a bias voltage is placed between the inner thimble wall and the central electrode. So in between here. Charge is collected at the central collecting electrode, which then flows out to the electrometer. A voltage called the bias is placed between the inner thimble wall and the central electrode. The central electrode is sometimes called the collecting electrode. If the central electrode is made positive, then any negative charge produced in the cavity by the passing of ionization radiation will be attracted to it. It then flows to the wire, attracted to the central electrode, and then will be counted by the electrometer. Chambers such as this could be used for direct measurement of exposure, but is more accurate to calibrate the chamber. Radiation therapy clinics send their ionization chambers to the secondary standards laboratories, which are accredited by the American Association of Physicists in Medicine, among others. The instruments used by these laboratories are calibrated by NIST. These secondary laboratories are called accredited dosimetry calibration laboratories. There are 3 ADCLs in North America, and the calibration process will be described a little later. It is recommended that ion chambers used for external beam radiation therapy can be calibrated every 2 years. Ion chambers used for cobalt-60 therapy beam calibration are required by the US NRC to be calibrated every 2 years. Farmer chambers, particular type of thimble ionization chamber, is commonly used for external beam calibration. So this is an example of a buildup cap and a thimble chamber. This is a farmer chamber. This is the inside of a farmer chamber. Collecting volume is approximately 0.6 cm cubed. The central or collecting electrode is cylindrical with a diameter of 1 millimeter and is made of aluminum. The thimble wall is made of graphite. The PTCFE material is an insulator. I forget exactly what that stands for, but it's a pretty long name if I remember right. So anyway, there's all that. The collecting, we just went through all of that. The cost of a farmer chamber is about $2,000, so don't break it. The farmer chambers are often used in a water tank for beam calibration purposes. The current US megavoltage beam calibration protocol, TG51, requires beam calibration of water as opposed to a solid material such as polystyrene. Under these circumstances, the buildup cap is removed and the chamber must be made waterproof. Newer farmer chambers are inherently waterproof. Those that are not can be placed in a specifically fitted rubber sleeve although a 1 millimeter thick acrylic plastic cap that fits snugly over the thimble is recommended. So, plain parallel ion chambers or flat cavity. Farmer chamber has a diameter that's too large for measurements in regions where dose is rapidly changing, such as the buildup region or in electron beams. The large inner cavity can disturb low energy beams and therefore provides inaccurate readings. So to solve that, plain parallel ion chambers are used. They have two thin, closely spaced parallel collecting plates or electrodes. Such chambers are sometimes called pancake chambers. One of the electrodes is a thin window through which the radiation enters the chamber. The entrance window is made of a foil or plastic membrane that is quite thin. This is what it looks like. For this reason, one should never touch the unprotected entrance window of a plain parallel chamber. Therapy plain parallel ion chambers typically have a 2 millimeter spacing between electrodes. It's pretty small, and a collecting diameter of 5 millimeters. This provides high spatial resolution in the direction parallel to the radiation beam. So you got a Marcus chamber. Here, the spacing between the electrodes is 2 millimeters. The entrance window is only 0.03 millimeters thick. A waterproofing cap is shown at the bottom center. So if you look at it a cross section, you've got your collecting volume here, you've got your thin front window, you've got your guard ring, ventilation hole, collecting electrode, and then goes out to the electrometer. Now, the charge collected by a therapy ionization chamber is measured by an electrometer. An electrometer provides a bias voltage between the electrodes of the chamber. A typical bias voltage is 300 volts, and it measures the charge collected. The amount of charge collected is typically on the order of nanocoulombs. Very tiny amount. The electrometer is connected to the ion chamber by a cable that has 3 concentric conductors, and that's called a triaxial cable. So, beam calibration protocols require measurement of the radiation-induced charge to an accuracy of about 1% or better. That's pretty stringent, so a number of small corrections must be made to the electrometer reading to determine the actual charge appearing in the ion chamber collecting volume as a result of an irradiation. The actual reading of the electrometer is called a raw reading, or MRAW. This reading must be mathematically corrected for the number of small effects so that it corresponds to the true ionization charge produced inside the ion chamber by the radiation. So, measurements made with a calibrated ion chamber are only as good as the electrometer that is used to measure the charge. The electrometer may not accurately measure the charge that flows into it. As an example, when the electrometer reads 1 nanocoulomb, perhaps the charge actually collected is 1.003 nanocoulombs. In this case, we can correct the electrometer reading by multiplying by an electrometer correction factor of this. Per reading, the value of the P sub elect can be provided by an ADCL, and an electrometer should be calibrated every 2 years. If an electrometer and an ion chamber were always used together, they can be calibrated as a set. And the cost of that calibration is about 180 bucks. Well, it was. The number of ions generated by a fixed amount of radiation would depend on the mass of the air inside the ion chamber. The greater the mass of the air, the more ions produced. If air pressure should increase, the mass of the air will rise, even though the volume remains fixed. If the temperature should increase, the mass of the air will decline. Ion chamber calibration is referenced to a temperature of 22 degrees Celsius and an air pressure of 760 milligrams of mercury. This pressure is the nominal atmospheric pressure at sea level. If the temperature and pressure do not have these standard values, then a correction must be made. And that correction is done using this particular formula. And again, remember your pressure and temperature units. All of this is based off of the ideal gas law. So the temperature and pressure correction can be the single largest correction to the raw electrometer reading. It can easily be 4 to 5% moderate elevations, and even higher than this is in mountainous regions. The calibration or the correction factor is 1 when these values are basically the values measured at sea level. As the pressure increases, the mass inside the chamber rises. Therefore, the amount of ionization goes up and the reading increases. As temperature goes up, the mass inside the chamber goes down, and therefore this must go up to compensate. This is why it's necessary for radiation therapy departments to possess a barometer and thermometer for determining this. During routine measurements, the collecting electrode of the ion chamber has a certain polarity. If the polarity is reversed, the magnitude of the electrometer reading may change. The multiplicative term corrects for this. This correction is generally less than 2%, so a piece of pole somewhere between 0.98 and 1.02. It is evaluated by making measurements at one polarity and then reversing it and repeating the measurements. Not all the charge produced by radiation inside an ion chamber is collected. Ionizing radiation produces ions of opposite signs. These ions move under the action of the electric field inside the ionization chamber. The positive ions migrate towards the cathode and the negative towards the anode. When the ions are collected at the electrode, they produce a signal that is measured by the electrometer. During the time that it takes the ions to move, some small number of positive and negative ions will meet and recombine, and therefore some charge will be lost. The larger the number of ions produced per volume, the more likely this process is to occur. Therefore, the effect is most pronounced in radiation beams of high intensity or dose rate where the ionization density is high. The lower the voltage between the electrodes, the longer it takes for the ions to be combined, and the more opportunity there is for recombination. If the charge collected is denoted as Q, and the charge produced is just Q, the ion collection efficiency can be defined as this: charge collected divided by charge deposited. So the charge collected divided by the charge produced in an ion chamber as a function of the applied bias voltage, which is what you're seeing here. The green curve is for a low intensity beam and the blue curve is for a high intensity beam. So you can kind of see the difference there. So the green curve, you can see here, as the bias increases, you're getting up close to saturation. Then that's for the low intensity. For the high intensity here, you're seeing it gets closer to the saturation here, but the bend doesn't quite take a sharper turn here with this as it does with that. This number is always less than or equal to 1. The amount of recombination depends on the bias voltage between the electrons in the ion chamber. At high bias, almost all of the charge produced in the chamber may be collected, and this is called saturation. The electrometer reading must be corrected for recombination. The correction to the electrometer reading is the reciprocal of the collection efficiency named P ion, or 1 over F. This is always greater than or equal to 1. It's typically less than about 2%. So roughly it's less than 1.02. The value of P ion is determined by making measurements at a bias voltage of 300 volts, and then again at 150 and comparing the measurements. It's possible to estimate this value, although we don't just go through that and discuss it here. You may wonder why we just don't increase the nominal 300 volt bias further to eliminate recombination as much as possible. If the bias is set too large, gas multiplication will begin to occur, and the chamber no longer acts as an ion chamber. After all the corrections discussed are evaluated, the charge produced by inside the ionization chamber by ionizing radiation under standard conditions can be related to the value m raw from the electrometer display as follows. Basically, you take m raw and you multiply it by all of these other factors. And that is what this process describes here. So now, survey meter ion chambers. So a survey meter is a sensitive instrument designed to detect the presence of radiation, usually photons, and to provide a rough measurement of the radiation rate. The corrections described in section 8.3.2, the previous section, are unnecessary for survey meters. Radiation survey meters are portable, handheld, battery-operated radiation detectors. There are many different types, and one type of survey meter contains a large volume ion chamber. A collecting volume of 500 cubic centimeters is typical. Compare this to the 0.6 cubic centimeter of a Farmer chamber. Much larger volume makes the chamber a very sensitive survey instrument. Ionization chambers have a relatively flat energy response over a wide range of energies, which is what this is trying to describe. Energy response of an ionization survey meter. This is how the reading varies for a fixed exposure rate as the energy is changed. The energy response is slightly different depending on whether the radiation enters the meter from the bottom or the side. The energy response is flat for energies above 100 keV. The flat energy response makes this an accurate instrument over a wide range in radiation energy. So an example of a survey meter ion chamber is the Victorine 450P, which has an operating range of 0 to 5 ringgits per hour. Chamber volume is 300 cm and is filled with a pressurized gas at 6 times normal atmospheric pressure. This increases the amount of gas inside the chamber. So for a given exposure, the charge produced will be 6 times larger than that for a non-pressurized chamber. The chamber walls are made of a conductive plastic with a wall thickness of 200 milligrams per square centimeter. The bias potential is 90 volts and is derived from two 9-volt transistor batteries. The ionization chamber survey meters are somewhat slow in responding to changes in radiation levels, and detectors based on GM tubes are better for finding lost radioactive sources or detecting contamination because they are very sensitive and respond quickly. Ionization survey meters tend to be more accurate in the readings for a large variety of isotopes because of their flat energy response. Proportional counters operate at a higher bias voltage than ion chambers. As the bias voltage is increased, ions liberated by radiation are accelerated towards the collecting electrode. If the bias voltage is sufficiently high, the accelerated ions may themselves produce new ionization. This process is called gas multiplication. The gas amplification factor is the amount by which the original ionization charge is increased by gas multiplication, and it can be as high as 10 to the 6th power. The amount of charge produced by the passage of radiation through the proportional counter is equal to the original charge produced by the radiation multiplied by the gas amplification factor. So the total charge collected is proportional to the original charge produced by the radiation, and hence the name proportional counter. This allows for the possibility of determining the type of radiation or particle. Since gas multiplication is desired in these counters, the gas that is chosen to fill the sealed chamber is selected for maximum acceleration of free electrons. Xenon and argon are usual choices. Proportional counters are not widely used in radiation therapy except for the detection of neutrons. And this you've probably seen before, the GM counter. is the radiation detector that most people have heard of. Consists of a tube, which is an actual detector connected to a counter or rate meter. The counter or rate meter is sometimes sold separately from the tube. In pocket models, the tube is enclosed in the housing. A Geiger-Mueller tube is used for survey meters. Very sensitive for gas detectors, but not very accurate. They are designed for maximum gas amplification. So in other words, if you're looking for a lost radio active source, this is a good way to try to find it. Counter sometimes has a loudspeaker that can produce audio clicks corresponding to every count. It can be useful when one cannot observe the meter continuously, but it can be unnerving to those who are not familiar with normal levels of operation. The rate meter usually reads in milliroentgens per hour or counts per minute, and it is typical to have a range of 0.01 up to 1 Roentgen per hour. Some meters have multiple scales. The response time can be adjusted, slow or fast. The needle can fluctuate rapidly as the counter registers individual counts, particularly at low radiation levels. It is useful under these circumstances to set the response time to slow. It consists of a cylindrical tube, and this is a thin end window GM tube. The anode runs coaxially down the tube, and the cathode is the outer shell of the tube. For detection of beta particles, a thin entrance window is needed so that the betas can get inside. The GM tube is operated at higher voltages than a proportional counter. The passage of a single charged particle can cause a pulse. Of course, many photons can pass through the wall in the gas without interacting or setting a charged particle in motion. When it traverses the interior of the tube, the high voltage causes avalanche ionization, leading to a large pulse of current. And all pulses have the same amplitude, and therefore no energy discrimination is possible. So a single ionization event can cause multiple pulsating discharges that will register as spurious counts. The multiple pulsing is caused by ultraviolet emission from positive ion collections within the wall of the detector. The UV interacts with the gas in the detector to produce additional ions. Prevention of such spurious counts is called quenching. There are two methods. The first uses the addition of a quenching gas, such as a halogen, which absorbs UV photons without becoming ionized. The second method is to electronically reduce the anode voltage momentarily after each ionization event is detected until all positive ions are collected. When it occurs, positive ions and free electrons are created. Free electrons are quickly collected by the anode. In contrast, the positively charged ions have a much greater mass and move slowly. During this time, the electrons are collected, the ions hardly move. This leaves a sheath of positive ions between the anode and the cathode, reducing the electric field inside the tube and thus inhibiting further avalanche ionization. The positive ions must migrate to the cathode before the electric field can build up again for subsequent avalanche. This leads to a minimum time between detectable pulses called the resolving time. The time scale is on the order of 100 microseconds. During this period, the counter is insensitive to ionizing events. It is possible in principle that in a high intensity radiation field, a GM counter can become saturated and read anomalously slow. Saturation may occur at an exposure rate of 1,000 milliroentgens per hour, or perhaps even lower. Meters are usually designed to peg at full scale under these conditions. The user must be aware that it's possible in a very high radiation area that a GM rate meter may read low, and they're not recommended for radiation surveys of linear accelerators because LINAC beams are pulsed. The pulses are brief and therefore of high intensity. So the energy dependence of a GM detector can be plus or minus 30 for 50 keV to 5 MeV. If accurate measurements are needed, The GM detector should be used for the type and energy of radiation for which it was calibrated. Very sensitive for a gas detector because of avalanche discharge. The passage of a single ionization particle can trigger a discharge. GM counters are mostly used as survey meters and are very good for locating radioactive contamination or finding lost radioactive sources. And the disadvantage is there is no energy discrimination. So this graph right here just summarizes the behavior of gas ionization detectors. At low applied voltage, there's a great deal of recombination. Higher voltages, saturation is reached. In this region, the ionization chambers are operated. As the voltage increases further, ion multiplication occurs and the signal becomes proportional to the original charge produced by the radiation. This is where you operate your proportional counters. At higher voltages, avalanche ionization occurs, and we reach the conditions under which the GM tube is operated. If the bias is increased further, spontaneous discharge or spark occurs. Here are a couple more disadvantages due to the resolving time. It is only possible to measure low count rates, and because they register counts and due to the energy dependence, they're not very accurate for quantitative work. So that's it for the gas ionization detectors. In the next lecture, we'll go over the solid state detectors.